Okay, so it should say live. It says we're live, but it's just recording right now because this is a private one.
Mm-hmm.
Um, so now it's recording, so we can have a copy of this. I can send it to you.
Thank
Um, Stop recording because that's one of the things because it's trying to share, but I think OBS it uses those
No,
particular
it wasn't a
resources.
conflict. It was just that I didn't click. I didn't select the screen that I wanted to share. But it's good now, so I can share now.
Okay. Oh, there we go. I see it. All
Okay,
right.
got it.
Let's see what we got.
So quickly, I would like to have more time today, but I really don't. But let me try to go over quickly of the things
Sure.
that I wanted to share with you and have your thoughts on. Um, I'm gonna use my Medium profile, the articles
Hmm.
that I already wrote to have a guide.
Yeah.
The
Well,
first,
that's basically why I do the YouTube channel to kind of keep track of my thoughts. Is I need to start a medium because writing is it's so important, man. It's so important.
I
And
don't see you now. Let me see. Oh, here you are. Let me see. Um, remove this a little bit. Okay. Let me go back to my profile quickly. Find the right article. So I'm gonna start with the one that questions the mechanism that give rise to the Hawking radiation. So
okay,
for what I know, the limited resolution that I have on the phenomena is that you normally have quantum fluctuations in space-time, and
yeah,
particles and antiparticles arise from those fluctuations
they
of
come
the quantum.
together, they annihilate, they do all these different things following the Feynman diagrams. Yep, yep, yep.
Okay, so near the event horizon of a black hole, it happens that what the antiparticle of a particle falls inside the event horizon.
Yeah.
So that results in the particle escaping in the shape of Hawking radiation, in the form
Hmm.
of Hawking radiation. That's the temperature that the black holes irradiate into space. And do you agree with me to that point?
That many people believe that. I don't think it's actually ever been proven, but
No,
many
not yet,
people.
not yet.
Okay, okay, yeah, you don't know, but it's very interesting because essentially the equation. Uh, I'm probably thinking of it a little differently. Maybe it was the entropy equation, which equates out. It's almost the exact same equation as the UNRWA effect. Apparently,
Okay,
like there's a very minor
I'm
change in
not
there. But no,
familiar.
no, I'm familiar. I'm familiar. Yes.
So yeah, this is black hole evaporation, the phenomena
Hmm.
that results in black hole evaporation. So if this is real and if this happens, my question comes from the fact of how does the particle that escapes in the form of Hawking radiations is informed that its antiparticle fell inside the black hole. So there has to be an information exchange mechanism that is able to overcome the escape velocity of the black hole and is able to inform the escaping particle that something happened to his antiparticle.
Yeah.
So this might be explained by the entanglement effect that everybody says that is independent from the from the limitation of the speed of light, but there might be something else in there. There might be a particle, even smaller particle, that is informing or exchanging of some kind of force that informs that the antiparticle fell into a black hole and is able to overcome the escape velocity of the event horizon.
How,
And
how
the other
how can something go faster than the speed of light? That's supposed to be a speed limit. That's a very good question.
Okay, so there is a mechanism there that is informing the particle, despite the fact that the escape velocity is the speed of light. So that is the question that I have there. How is the system informed that something weird happened to the antiparticle in the future of the? Normally, those two will cancel each other. In the
Hmm.
absence of the black hole, the particle and the antiparticle will cancel each other
They
out.
pop in, they pop out of existence, they
Yeah,
annihilate, yada yada.
yeah. But something happens, and then the future of a particle that was supposed to be extinguished, this was supposed to be disappear
Mm-hmm.
when the particle was created. The future changes in the presence of a black hole, of the event horizon. So, on top of the question of which mechanism is informing the particle that the antiparticle fell inside the black hole, my other question related to causality is the future of the particle that was supposed to be extinguished and now escape in the form of Hawking radiation, is the future of that particle change when the particle was created, or did that particle had to wait for something to inform that the antiparticle fell inside the black hole? You follow me?
That you know what?
So let's
I
say
w-
you and your
oh
brother,
yeah,
you both came out to the world, and you were you and your auntie,
right, right,
you
right,
both
right.
were born. You were supposed to cancel each other out in a very
Mm.
brief amount of time, but you all of a sudden you realize you were informed that your auntie brother fell inside the black hole.
Mm.
So were you in the moment of your creation immediately turned into Hawking radiation, or did you had to wait for the mechanism to inform you, and then your future was changed after you were informed? See what I'm trying to say? Is the transfer of information immediate when the two particles are created, when they emerge, or it is there a kind of delay, some latency between the creation, the falling into the black hole, and the information going to the other particle? Okay, you can now escape as Hawking radiation because your antiparticle fell into the black hole. Do you
That's
follow me? Do you follow what I'm
I no no I you just generate several more questions that now I
saying?
have as well, and that no that this is a beautiful thing. I'm gonna you don't mind if I smoke, dude, because I feel like I need some
Go
nicotine
ahead,
to
go
try to
ahead,
process this.
go ahead, go
Okay,
ahead.
I love that you asked that because shortly before I was listening to one of Professor Susskind's questionings, was I think it was Brian Green for about a year or so ago. Every once in a while, the algorithm will bring me back to things that I listened to
Uh-huh.
that I didn't really understand what they were, but now that I have a little bit more understanding, it makes more sense. And a thought occurred to me probably about 2 hours ago, which is
Hmm.
it's fantastic you asked this, is the effect that you're almost describing there. It almost sounds like the black hole is functioning as an observer.
Maybe, I don't
You
know.
know, no, like, because the way we often interpret things, and I could be completely wrong. This was an idea that popped into my
Yeah,
head
we're playing with ideas. Yeah.
because that's the thing. It's like, okay, we have this black hole. It's like, okay, like when we do a measurement or something, the wave function collapses, and people say, "Oh, we have many worlds. Could that happen? Maybe. I have no idea." But we're perturbing the wave function in a way that it wasn't necessarily intended to. Now you could say maybe that was going to happen anyway, but interesting things happen, especially since we're only at least on the quantum scale right now. We can basically account for momentum or position. We can't do both. We can do
Mhm.
one or another. That is fascinating. But I'm thinking there, I'm like, okay, normally these things would go there. What's happening? One particle's falling in, the other is going out there. The normal answer that's generally accepted, Professor Susskind says that the reason there could be some coherence between them, they call that ER equals
EPR, yeah.
EPR. Yeah, it's the entanglement thingy there. Um, that is fascinating because people are like, well, you can't go faster than the speed of light. Interesting thing, if you play around on Wolfram Alpha long enough, there actually is something faster than the speed of light.
Oh, really?
About a couple orders of magnitude. I think it's the speed of causality. they have it there, and I'm like, Wolfram Alpha is pretty well curated. I'm like, why is this here? I think somebody had predicted it and made it onto the archive there. I'm like, and it wasn't just a little it was several orders of magnitude faster than the speed of light. So it was either the speed of information or speed of causality, something like that. So that's already kind of been predicted, even though a lot of folks may not necessarily accept that. I tend to kind of believe there's something to that for my own reasons. Okay.
Yeah.
So which I know we have a limited time. Which
No,
one do
don't
you?
worry, don't worry.
Which one do we want to address? Do we want to address how entanglement potentially works, or?
I would like to leave you with this question, moving to the other couple observations that I have, and then maybe you can follow up. Read a little bit.
We could always do this again and stuff. I love talking about this
It's
stuff
a pleasure
because this is how I learn. Go on.
And eventually, I would like to relay these questions to somebody who has a technical background, the proficiency to answer them mathematically, because I just bought the Sean Carroll book that has all the relativity, the GR in, I don't know if quantum mechanics as well, fundamental equations, and I'm going to start getting into them now. But formally, mathematically, I haven't done anything yet. But I feel like it comes really natural to me I'm a very visual person, I think, in terms of images, and having like a background in motion graphics and design and kind of 3D animation helps me a lot in visualizing the processes, and visualizing the dynamics, because this is
I may reach out to you for some work then.
Okay. I feel like this comes to me, the GR and this kind of things come to me quite naturally. I like it a lot. And since I was a kid, I really liked them. But I never took myself seriously enough. My scientific thinking, I never took it seriously enough.
Don't doubt yourself, man. Don't doubt yourself. Because it's fascinating. I have a thing that I need to premiere, because I actually just spoke with Kotov. He's one of the other kind of trolly people in some of like the Wolfram chats. And he happens to be a Russian individual, and it's fascinating because he was explaining to me the way he thinks is the exact opposite. He thinks almost computationally. Like that's what comes natural to him. He tells me he thinks in English, he writes in English, but Russian to him, like, because he'll think in English, then he naturally speaks in Russian, but then he needs to translate into English, which comes a little bit differently to him. No, but that makes sense. Thinking visually is so useful when it comes to GR, because if you're going things are bending and stuff like that, if people don't think in those terms naturally, I mean, there's already a communication barrier. So go on. You were talking.
No, I also have a background in computation and in programming and coding a little bit when I was younger. So that the computational notion of Wolfram also is kind of familiar and comes natural to me.
Wolfram Alpha, just play. Every once in a while on my breaks, something will come to me. I'll just look something up, and even if I don't make any ground, I may find one term. It's like entropy. What is this? Is this like the inverse of entropy? What is it? Like, you'll just hear these different things. And that's the beautiful thing about the internet. Is because now you can hear something. You don't need to go to the library. You can literally just pause whatever you're listening to and just look it up. It's wonderful.
Yeah. No, I love the work that Wolfram has done. It's amazing work. So the notion of space-time being like pixels always came to me naturally, because I was a gamer, John. From
I often kind of think the same way. Yep, go on.
So it came really natural to me. And I do have a note here that I made that I wanted to talk to you about, the notion of a pixelated universe, like the atoms of time, atoms of space.
Atoms of space. The EAMS. I remember because it's my moniker minus the M.
All right. I have a serious question about that notion.
Okay.
I'm gonna draw here a little bit. Tell me if you can see my screen here. Can you see it?
Gotcha. Yep.
Okay. So let me erase this quickly. And let me paint with a bigger brush. So we have the notion of atoms of space, right?
Yeah.
And these atoms are supposed to be four-dimensional. Well, three-dimensional in terms of distance and length and depth, right? So I think they can be represented as a cube, most likely, right?
Yep.
Have you heard anything more than this?
Jonathan models it via tesseracts or the hyper four-dimensional tetrahedron and stuff like that.
Okay.
But yes, we're operating on the assumption that space, they call it discretized. Basically, it's discrete. Like there is an actual limit to it. Yes.
Okay. So this might not be the case, but let's play with this anyway.
Oh yeah.
Let's say that we have these atoms of space.
Yep.
Sorry. Let me fix it. Push. We have these atoms. Let me. Push.
See, this is why I like technology. Just as I look at this, I'm like, oh, looks like we're building with blocks again.
Yeah.
I feel like if they just renamed quantum mechanics like
space-time Legos.
Exactly. It's like nano Legos or something like that. It's just like, yeah, it's complicated. We don't necessarily know what's going on really, but it's like, I feel like as soon as you throw quantum, people get scared and run away.
Yeah.
And that's such a shame.
Let's say that we have this structure, right?
Yeah.
So we could say that the minimum amount of distance and space or distance and time that can happen. I mean, the size of these atoms is one Planck length by one Planck time, right?
It's Planck length by Planck length. So it's the Planck. We're doing the Planck volume here.
One Planck length by one Planck length by one Planck length by one Planck time. If they are four-dimensional, I would guess.
Okay, I mean, we might not even really necessarily need that, but I mean, maybe. I don't know.
Let's get away. This is a question related to space more than space time. So let's get rid of time in here. Let's work with
just assume three-dimensional. Okay.
Three dimensions of space. So my question is, let's say that I have a particle that is moving, or a wave, or whatever it is, moving through this grid of space-time, right? And let's say that I want to go from here. Let me change color. From here to here. Okay? Yeah. This is the trajectory that the particle would cover, right?
That's what we would assume.
Okay, let's assume that. Yeah, let's assume that. So this is fine. This looks fine. But if the particle wants to go from here to here, there is an aliasing problem because there is no straight trajectory. So the particle will have to go from here to here and here, or from here to here to here. And so this structure doesn't allow all the directions, all the possible directions in a straight path. You following me? So we can go from here to here, jumping diagonally. And this is a uniform motion. But if we want to go from here to here, there are more steps. From here to here is 2 steps in the middle, right?
Yeah.
In the same angle. This is the angle, 45 degrees with respect to the coordinates, for example.
But with the other one, there are a number of different. We could go through there, or you could do one step over, or one step up,
Then you
one
will have
step
to take,
over. There are a number of different ways you could go through there. Yeah.
so this will be the trajectory then. Here or here. So apparently there is a change in the angle that the trajectory has to assume in order to reach its destination. So it wouldn't be straight. You following me a little bit?
Yeah. No, no, no.
They,
I see what you're pointing out, and it's interesting. I think this may also be one of the other reasons I do the whole path interval thing, because it's like, well, we could do all these different things here. We're just going to try to focus in on what seems to be the easiest there. But no, that I like the fact you're talking about the angle there, because that's something we could actually try to actually quantize or
uh-huh.
actually work some computations
So,
with.
and this is on a very short scale, 4 by 4. So if you
Right.
have a much bigger grid, the trajectory will be a lot more complicated, because at some points you will go through like three. You will eventually have to touch on more pixels depending on the angle.
Well, it's funny. It reminds me of the old antidote. I apologize for any
Go ahead.
potential racism there. They say I have the no true Scotsman thing. It's like, well, nobody's actually fully Scottish, or no true
Go ahead.
Irishman or something like that. I'm like, is there any such thing as an actual straight line?
Yeah.
We
So
can get you
this
thinking
will bring
something.
this will bring that kind of question of geometry, and how is the particle informed that the jump, this is the time to jump to the other column, or to the other reference point, to the other atom of space, because there is an aliasing problem here. Are you familiar with the concept of aliasing?
Say it one more time.
Aliasing. I don't know if that's let me find it here.
Uh,
In computer graphics, you have this problem. Sorry.
oh,
Um,
a laser. Okay.
where in computer graphics you have this very same problem. Let me go back to the screen. Sometimes you have to make a diagonal line, but the pixels have a limited resolution. If you want to go, let's say that you want to make, let me go back. If you want to make a 3 pixel diagonal from, let's go the other way. This is wait a second. One, here, 1 second.
Is this the effect that comes up that when you have a camera looking at the wheel of a car, it appears to spin backwards?
That's rolling shutter. Rolling
Okay,
shutter.
okay, okay.
Rolling shutter, because the scanning rate, the scanning frequency of the sensor sometimes coheres with the motion, and then the wheel move maybe
Oh,
90 times a second. If you're scanning at 60 frames per second, then there is a 1.5 frame of decoherence
so it's an
there.
illusion. That's not what we're talking about. Okay, okay,
No, no. The effect that you're talking about is called moire.
okay.
Is when in cameras, when you have an object that has a resolution which is higher, a pattern that is higher than the sensor resolution,
Hmm.
the sensor has to skip lines. So you're losing information from the original image, and you can get this kind of weird meshes, moving meshes, if you're
Okay,
filming something that has a resolution higher than the sensor is able to reflect. So
gotcha.
let's say that you have a grid of black and white dots on maybe a wall, and those grids will be probably reflected on a 100 megapixel camera.
Right.
And if you have a 50 megapixel camera, you are losing half the resolution. So it might be
Mm,
the case that due to the fact that you're losing half the resolution, you might lose all the white squares. Let's say that you're filming a chessboard
Right, right.
that require very tiny squares, black and white squares, and it
Mhm.
requires 100 megapixel resolution sensor, but you
Yeah.
have a 50 megapixel resolution sensor.
Mhm.
So the squares on the keyboard on the board are 1 pixel, half a pixel by half a pixel in terms of your camera, you know.
How does it
So in
determine what it's
reference to
going to
you,
be?
so the camera will have to be skipping a whole line on the vertical and the horizontal, because
Mhm.
the amount of pixels are not enough to reflect the resolution of the object it's filming. That
Mhm.
only happens with very tiny, not necessarily tiny, but that happens when the pattern that you're trying to film requires more resolution. If you're filming a flat wall, a flat color, you don't
Mhm.
have that problem because the pixels that are being skipped are the same as the other pixels, so you don't see a difference. But if you have this kind of pattern that requires higher resolution, you might be missing vital pixels, you know, that changes the aspect of the object. It's a little bit weird to explain it to somebody who's not very
No,
familiar.
no, no. I mean that makes a lot of sense to me. Just because I'm thinking it's like, okay, if I'm the size of like one of these cubes, let's say I'm a particle or something like that,
Uh-huh.
I'm going through. It's like, well, if we needed higher resolution, but we're at the absolute limit, you can't get any smaller. I think a lot of this is possibly solved because the Planck length is at 10 to the negative 35 meters. Most particles, even the electron in and of itself, I believe it has. No, actually, no. I did this before. No, its radius is well. It depends on if you're using. I think it's 10 to the negative 15 or 10 to the negative 11, somewhere within that order of magnitude.
So
There's a
it's not
difference.
only bigger than a Planck length. Okay.
Yeah, well, what I'm saying is most particles or waves, typically, to my knowledge, are going to be a lot larger than the Planck length or Planck volume. So a lot of this, they'd be covering maybe 4 or 8 or however many of those. I think that's how they kind of get around it. But you still bring up an interesting point: is if space is discretized, how does it know whether to go to this one or that one?
There is a
And that,
limit. If a space is discretized, there is a limit in the directionality that the particle can take, because or there is some weird effect that is happening. Let me, oh, what's happening here? Okay. Um, because if the particle is going, let me finish this one. Two, um,
yeah,
uh, push, three here, push, four, push. Um, let me,
I've already bookmarked this page because this is
hmm.
fascinating. It's no,
So
this is why I love talking to people, because this just one thing. If anything else I take away, this one thing is something that's been in my mind. I've been trying to think, how might this work, and just it's funny you bring up the pixel thing, because every once in a while I'll be thinking about these things, and then I'll look at a television screen. I'll be like, is it really much different?
no, maybe not.
It,
Maybe not.
it's I like to use the classical, maybe if people like to say, it's like, well, if we were two-dimensional spaces kind of enclosing each other, I'm like, I don't know, sounds like a record player, like that whole ADS CFT correspondence that Jonathan was kind of teaching me about. I'm sitting there, I'm like, well, if we had the quantum field theory on the boundary and general relativity could naturally emerge there, if we could figure out what the quantum field theory, like the grooves in the records itself, I mean, it sounds like a beautiful thing. This is why I love this. But I'll go on. You have it. You have another point.
Yeah. So basically, my thinking is that there must be a way in which every two atoms of space, any given two atoms of space, are connected in a kind of direct way. Maybe there is a hyper surface or hyper shape or whatever, because Eric Weinstein talks a lot about spinors, and I believe that one of the property of spinors is that every point on the figure is connected to every other point. So if that is the case, maybe every one of these pixels is connected, doesn't have a contact surface between one and the other. Maybe they are, all the points in one pixel is connected to all of the points in the other pixel. If that is the case, then you probably wouldn't need to follow a straight path in the sense of us, because if point 273.5 is connected to point 273.5 on the other atom of space, then information or whatever, the wave or whatever it is, travels independently of the internal trajectory that it might take to that other point, and that other point is connected to the other point. So we're talking about this aliasing here because in our notion of classical geometry and classical maybe diffraction and incidence angles, we are used to, if these atoms were a prism, like a glass prism or a crystal or whatever, they will light or the photon or whatever it is will have to travel in a straight path, and if that path changes, then it would be some kind of diffraction or change in the trajectory. Maybe that is not the case. Maybe an event can travel in an arbitrary fashion between all these atoms of space without suffering from any kind of diffraction or reflection or distortion in the path. But my notion is, the notion that I have is that energy is kind of the effort that a particle has to overcome to move itself from one atom of space to the other one. So things follow straight path in nature, normally in the absence of space-time distortions, because that is the least amount of energy that an object has to spend to go from point A to point B.
Right.
There are a lot of questions here. I don't want to overwhelm you, and I don't want to confuse myself in the way that I'm explaining them. But
No, this is why we're gonna have a record of this, so we can actually go back and everything. But no, ask away, man. I love this.
okay, so let's say that it takes a certain amount of energy to go from here to here. That would be a straight path from A to B. But if at some point, this is too low resolution, but if at some point I have to move from here to here, see, from here to here, it takes only 2 steps, right? But from here to here, you are keeping the angle constant, and then you have to be making a switch, because if you keep a straight path from here to here, from here to here, you are basically going necessarily over 3 atoms of space instead of 2 atoms of space. Do you follow me? Do you agree more or less? In
Yes.
terms of geometry,
I
not
love it.
necessarily in reality. So
No. This is fantastic. This is
let me
fantastic.
let me write it again. Particle A, particle purple, goes from here to here to here in 4 steps. I mean, 2 intermediary steps. But if particle green wants to go from here to here in this path, let's assume that these atoms of space are closer to each other. Not necessarily, but they might be. We're assuming that they are close to each other, right? Although I have the theory that maybe dark energy is some kind of force that is pushing the atoms between themselves apart. And gravity pulls them back closer to each other. So to me, there is a difference between space-time and dark energy and gravity are two forces that are trying to push apart or closer these atoms of space.
When you're doing that thing with your hands, it kind of reminds me of the beating of a heart.
Yeah, the universe is beating.
Kali likes using the cardioid as a representation of what we know as universe, and I mean, cardioid naturally implies heart, and I've been thinking about that, and crazy thing is that might kind of explain a lot. It's also fantastically beautiful.
So the contradictions in this system that I'm playing with come from the fact that you either keep the amount of steps fixed or you keep the angle fixed. You either conserve the energy or to keep the angle and vary the angle of the movement. Let's draw it back. Let's draw it again. So particle purple goes from here.
We would either need to conserve the number of steps or conserve the angle, because something needs
Yes,
to be conserved there. Okay.
yes, because
Oh.
then particle green has to go from here to here and then decide this trajectory or this trajectory or this trajectory and this trajectory. So all of a sudden there is a kind of
It's something that's closer, but it requires an additional step rather than
so
something that's
there is
further away.
all of a sudden playing with this model, the um, the double slit problem shows up in here because at some point a particle travels from 1.4 to 4 let's 1,4 traveling from here 1,4 to 2,1 will have too many paths that they can decide to move from. You see, too many different trajectories available for it.
This is a great representation of, at least for a toy, at least for me, just in my position of thinking, it sounds like your position of thinking. I'm like, I mean, is this entanglement? I mean, is this what it is? Is this the issue we're running into? Because all of a sudden it's like, well, that's close, so that's farther away, but we can communicate across that, and it seems easier. Why? Well, we're just using the angle there.
At
I
least
could
this
be completely
to me
wrong, but
as a distribution of probabilities, as a distribution of possible path. I don't know. That's why I want to. That's what I want to get in touch with somebody that works with one of these super experts. Maybe they can help me out with this.
what I would say is I would play on Wolfram Alpha and or Mathematica. I know. We want to go straight for it, and
Yeah,
I've been blessed enough to start getting in touch with some really smart people, and I'd love to just be like, "Will you do this for me?" But I know I have to do a certain level of
probably
work myself to get myself to a certain bit. Like I've spent the past year and a half playing on Wolfram Alpha to the point now where somebody could throw a random notation. It's like, did I get that right? It's like, I got it right. That was A angstrom units, not AU for gold. Okay, yes, that made more sense. So it's familiarizing yourself
yeah, and
with the different
acquiring the
material.
knowledge. Yeah, for sure. Um, so yes, this is more or less the kind of model that I'm playing with and what I'm finding incongruencies or incoherencies. Um, so we have the aliasing problem. Let me skip this one and go over the other quickly, just very quickly to show you.
Yep.
Mm, let me see here. Well, check out the alias problem in computer graphics later if you want to get
I mean,
familiar
I'm
with it.
just skimming this. This seems to. I mean, I just look at the little chart, the little wavy thing here. I'm like, all right, this. I mean, this sounds like a lot of issues that we run into within quantum mechanics. Again, I'm not a trained physicist, but it's sounding a lot of the same thing. We're talking about ways of observing things, and issues. And I'm like, if we're going to start saying that information represents our universe, this is just a natural path to follow. So no, very intuitive. But yes, your other thing
Let
you want
me
to
let
talk.
me let me hit the other one quickly. Um,
Oh, this is great.
let me go to profile. This one it might be a little bit might require a little bit more time, but I'm gonna try to explain it quickly.
Hmm.
Um, this one also has to do a lot with quantization and with the nature of space-time. Because what I'm saying is, let me use this same example here. You have a particle collider, right? And you are basically, what they are basically doing is getting a particle, accelerating the particle, and making it collide with another particle. I need to have some more detail on certain parts of the process, but um, for
What happens is a gravitational ripple and space time essentially contracts. Particle A going at 0.9999 times the speed of light. Particle B, what happens if there's this little dip and they're effectively going faster than the speed of light?
the question has to do with the fact that so far, what we take for speed is we take an object that came out from point A,
Mhm.
went to point B, or it's going to be on point B, and we measure the amount of time that it took the object going from point A to point B, and we consider that speed, right? It's the amount of time that it took an object to cover a certain distance. Um, I know that there are some reference frames reconsiderations that have to be in terms of general relativity. But what I'm saying, this is why I need some clarifications. But what I'm saying is that what I've noticed so far is that in GR, in general relativity, an interaction is not necessarily seen as a special case of speed. General relativity doesn't differentiate between an object moving around in space. Uh, what general relativity accounts for is the
GR don't care what you're doing. You can do your thing. GR is going to do its thing.
so an object has an energy momentum, has a momentum to it, has an energy to it. Um, from what I've been able to absorb, that the total energy of an object in terms of general relativity is equal to the mass of the object by the speed of light square plus uh, the momentum of the object.
Right. Yeah. And
So,
people forget those other two little bits there. I think those are important there. We seem to forget those. Go on. Yeah.
yeah. And when general relativity refers to speed, it's usually referring to speed, from what I know, in terms of the past of the object, let's say, or a given reference frame that is usually that of the object in the past. Let's say a relativistic particle is considered relativistic because it left point A and traveled to point B, or is traveling at this moment at a given speed in reference to the frame of the past, to the moment where it was a given amount of time um, uh, before. So let's say
Well,
we have,
that sounds like that wheel effect you were just almost kind of talking about there.
say that again.
Remember the wheel effect, the effect of the wheel, how it looks like it's going backwards. I mean, it's. I realize it's not the same thing,
Mhm.
but ultimately, it's like your reference frame, Matt. What's very interesting, and this is something I learned from Fractal Woman. I'll put her link to her YouTube in the little private chat here. Uh, but apparently, she's really big into electricity and everything, and she's been going back to a lot of the earlier papers that we kind of forgot existed.
Mhm.
And there was one thing that I'm still slightly boggled by, is that one of her videos, when she has an ether model, basically like you have like some medium, call it the ether if you would, and superfluid, whatever, And depending on where you're looking at the electric flow, the effects on the field, if you're on one side, it looks like it's going one way, but if you're on the other side, it looks like it's weird. It's weird. I'm still trying to get my head around that, but
Yeah.
that's what. Okay, no, go on. I'm sorry, I
Yeah.
interrupted.
Don't worry about it. So basically, the notion of speed that we have in general relativity, from what I know, is in reference to the past of the object that we are referencing in itself. So we have a given particle, and you have a reference frame of that particle against itself. So there is no the only non-relativistic motion that exists in the universe is the motion that you are having against your own past. So the speed of a particle might be relative in or maybe you have the speed of light, which is supposedly absolute, and no matter your reference frame, is always going to be 300,000 kilometers per second. But for every other object that we have, that we know of, or at least I have heard of, its speed is a function of the change of its position in regards to its own past. So the object was here a second ago, and now the object is here 1 second after, and then we have a relative velocity given the change in position and the change in time. Delta t plus, and not, let me not talk like that. Delta t and delta d, the change in speed and position in
Change
space
in
and
length
time,
over change in time. Yep.
yeah, is interpreted as a speed. Okay, and that accounts into the total energy of a given object, let's say a particle.
Mm-hmm.
But I from what I know in general relativity, the case is that you can consider if two objects are going to interact. Let's say in the case of a particle collider, you have one particle that can always be considered to be at rest. Let's say that two particles are going to interact, and you have one particle that be considered at rest, and all the motion happens in the other particle. And this seems to be arbitrary. You can consider that the particle that is being accelerated is in motion and the other one is moving. It wouldn't make a difference if one or the other particle is considered to be the one that is in motion, right? So what I'm saying is that in the case, at least in the case of interaction between two objects, the relativistic interaction between two objects, speed it should be considered as the change in distance between those objects that are going to interact in the future. So you shouldn't measure particle A going at 99.99% of the speed of light. You should consider that the distance that is separating particle A from particle B is reducing at that same speed. The delta between the two particles is what is important, not the delta of a particle compared to its past. So let's say 1 second, 1 second ago the particle was here, and 1 second after the particle is here, and the delta between those two equals to 99.999% the speed of light.
Yeah.
And then in the next millisecond, those two particles are going to collide. That is one way of conceptualizing speed.
Mm-hmm.
And that seems to be fine if you are measuring the speed of an object that is not going to interact with anything else.
Right.
But if two objects are going to interact, then what is really relevant is how quickly the distance between those two objects is changing. So there is a reference frame in itself when you are going to have an interaction that is intrinsic to the interaction in itself, because that is an event, a special event that is going to happen. So in general relativity, for what I know, doesn't make any distinctions between an object that is traveling freely through space and two objects that are going to interact. That is the same problem that is another contradiction that I see in quantum mechanics. It doesn't make sense to me that if two objects, two systems are going to interact, that the minimum amount of elements that need to be present in an interaction is two objects plus an observer. So to me, the minimum interaction that is possible in the universe happens between two systems. You don't have to have an observer to account for that interaction. So to me, this is difficult. This is difficult to explain, because you normally have to agree on a lot of terms and a lot of words, and then kind of establish a communication protocol in order to discuss these kind of things, because I'm using my own vocabulary here and my own arbitrary definitions that might not be
If
compatible
if
with the
if
normalization.
if only somebody was setting up a computational language that we could kind of use as this is why I love Professor Wolfram. Just
This needs.
now, and now
Yeah,
I'm okay. Let me just try to rephrase that. Um, it sounds like what you're saying is you're all right with particle A going almost the speed of light, particle B almost going the speed of light, but where, because now if those are allowed, they can smash into each other. Or are you saying that is something weird because at some reference point
let
it
me
would
know.
appear where it's
I'm not
meeting?
getting to the. I'm trying to make you, to give you the notion, just to give you the notion of uh, relativity traditionally being more about comparing the present of a given object, a present of a particle, with its own past, and calculating the delta in the change in space and time, and that becoming the concept of a speed. What I'm this is that is you have part. Let's go quickly back again over it. You have particle A, point A, moving to point B,
Yeah.
and the speed of the particle is given by the change in position and time.
Mhm.
Uh-huh. I'm proposing, or I'm playing with the idea that when you have interaction between two systems, the origin of the movement, of the motion, is not as important, or the reference that you should have for calculating the speed and the nature of the interaction is not so much given by the origin of the motion, or by the origin or the past of the particle, but it should be measured from the future interaction into the present. Normally, physics goes from the past to the present and even to the future. You are projecting into the future a
Mhm.
property that the particle has. So
The
let's
the
say
the the ter- the term, sorry to cut you off. The terms that they use is like past light cone and
Mhm,
future light cone.
mhm.
That's typically the vocabulary that they
Yeah,
use.
the
So what you're
Minkowski
saying
space
is
time.
we should consider more the future light cone rather than the past light cone.
Well, yeah, when you look when you look at it like that, is kind of what I'm saying. What I'm saying is, normally the future light cone is an estimation of the possible futures that a given object
Right,
might have
right.
in space time.
Hmm.
I will have to reframe that a little bit in
No,
using.
no, yeah, you use whatever. I mean, I understand. I'm just letting you know typically the terminology that's used. But
So,
no, go
but
on.
what I'm saying is that the interaction in itself, the collision between the two particles, has a light cone of itself. That obviously is
Yeah, yeah.
coherent with the light cone of each of the other two particles. So particle A has a light cone, particle B has a light cone. If you project those two, they will cohere in the future. And in that kind of same fashion, you have the interaction that is going to happen in the future, the collision between the two particles, and that interaction in itself has a past light cone that coheres with the future light cone of the two particles.
But the past light cone will be made up of the two previous particles, previous light cones, and that's interesting because now
the future
you're
light cone?
generating a new light cone that's going to be different in some way, I would assume, but it's going to. Oh, that's interesting.
I'm not sure. That's why my ideas need to
I
be.
mean, that's where my mind goes. I mean, that's just
I
what I
have to
thought of it.
assume that you are understanding what I'm saying, and you kind of have to assume that I'm saying what you think I'm saying as well, because it's our first conversation. We have this is not that easy.
Where is the collision's previous light cone or past? How do we differentiate that? Because that's only happening from the interaction, right?
So what I'm saying is that when you have a collision, a transfer of energy between two systems, I'm trying to conceptualize collision just as a transfer of energy between two systems.
Sure.
When you have that event, the for the universe, well, this has to be with the fact that how the universe cares about this phenomena, because maybe what is relevant for the universe is how the particle has been moving from the past into the future and how that event is going to happen. But maybe the universe cares the if the information, this is another kind of way of trying to explain it. If I accelerate particle A and it's going to collide inevitably with particle B, we can assume, if we look at many worlds theory, that in one of the universe of many worlds, that event is already pre-established, unless the trajectory of or the velocity or any of the qualities of the particles change. And that event in the future is one of the possibilities of the many worlds interpretation of quantum mechanics. So we have particle A is going to collide with particle B in 2 nanoseconds. Yeah. So in many worlds theory, you have a lot of universe when none of those particles collide, the speed changes, the trajectory changes. There is all kind of supposed distortions and different futures available for each particle. Mm-hmm. But if that is the case, the events in the future are kind of already established, and then the universe validates a given future depending on which conditions continue to happen. Let's say the speed remains what is supposed to be, the trajectory remains what was supposed to be, and then you probably have a distribution of all the universe. Let's think in many worlds terms. You have a distribution of possible futures. The one in which nothing weird happens is the most likely, and then everything happens as according to the laws of physics that we know, and at the end the most likely future is the one that eventually happens.
Yeah,
I'm getting a little bit too ambitious here, but the question is the event in the future already predetermined, and then the laws of physics obey the least energy demanding or the most mathematically probable set of events, or is the future indeterminate and constantly the universe is updating with the properties of each particle its own eventuality, and something happens without any other kind of predetermination? So what I'm saying here is the future of a particle that is moving through space and time already kind of predetermined, and the properties of the particles and the systems validate that given future that is already kind of predetermined and kind of pre-calculated by the universe and by the wave function. Let's say that the wave function is ahead of the eventuality, is opening possibilities, and then the events that happen make the wave function collapse in a given configuration according to whatever conditions were present on a given interaction, a given system. So you basically, let's say that you have a branch out of possibilities. Those possibilities reflect any possible change in the light cone of the particle. Let's say a particle has its own light cone, but according to many worlds, that light cone is open. Anything can happen, supposedly on many worlds interpretation from what I understand. And then maybe there is a restriction on the possible futures given by the fact that the possible futures available to a system is that which demand the less energy for the system. So in reality, you may have all the worlds and available futures for a system, and then the ones that collapse are the ones that demand the less energy from a given configuration of possibilities. So, but that is not the question. That is also that question coheres with the question of is the particle of the future of is the future of the particle that is about to become Hawking radiation determined beforehand, and the antiparticle falls inside the black hole and makes the wave function collapse in a given configuration? Or is this something that is uh, uh, let's say that the particle had a whole possibilities, a big light cone in front of it. That light cone wasn't necessarily previously calculated or determined by the universe. And when the antiparticle didn't meet the particle where the antiparticle was supposed to be, did that change the trajectory and the future of the particle that was supposed to be canceled out by its antiparticle? In that moment, when let's say particle A and antiparticle A were emerging this point, and were supposed to meet on the other point, and particle A got there and antiparticle A wasn't there, and then it escaped as Hawking radiation? Or did somehow the information about the fact that they weren't going to meet and they weren't going to cancel each other out already available for the particle in the moment where the particle emerged? See what I'm saying? I know it's difficult.
Oh no. We'll see. The thing is, it's a grand question because it almost sounds like it's like, all right, are things almost super deterministic in a way? Like, is everything just gonna play out? Is it all predetermined, or is a black hole in a way at the event horizon almost collapsing the wave function, seeing almost like an observer in a way? I don't know. I don't know. That's why I said it was a grand question.
So
I think, go on.
I don't want to steal too much time from you. I know you have been very generous with your time and your attention.
Oh, this is great, man. This is great.
But in the same fashion, you can have, let me go back to Photoshop quickly here. You can have particle green here that is going to collide with particle red here. This is a collider, a particle collider, right? And they are supposed, let's say that we have one more atom of a space here, because just to have an odd number. Let me go here.
Which program is that?
This is Photoshop.
Oh, I spent too much time on a Mac.
So we have particle green here and particle red here.
Okay.
Particle red here. they are going to collide with each other at 99.9999% the speed of light. I have another question, another important objection here in the way that physics is normally working, because we should be using, for to me, we should be using natural units. I'm gonna try to tell you why
Okay.
later, or as soon as possible. So expressing the speed between two systems that are going to interact in a relativistic fashion in meters per second, or whatever international units per second, doesn't allow you to think about it in the right way. We should be thinking about how many Planck lengths are being covered in how much, in which amount of time. Let's say we are using 99.99% the speed of light, but that speed of light is always expressed in meters per second.
Mm-hmm.
In reality, we should trying to express that in Planck lengths per second, or per Planck time.
Right, right.
So one thing that I have to find out is, um, I actually looked for it on Mathematica, but I don't remember, and I have to start taking notes, because I never take notes for anything. But this is so complicated, and the numbers are so ridiculously small and big, that one has to get acquired with the units and the amounts and the whatever. So the speed of light, when seen as the amount of Planck lengths that are being covered or traversed by a given amount of time, it completely changes your interpretation of an event and speed, because you cannot try to quantize a phenomena if you are using units that are not quantized. If you are thinking in trying to quantize the speed of an interaction, and the nature of speed, and the nature of space time, and you are using infinite numbers that can be divided infinite times, you are not really incorporating the notion of quantization in your own thinking process. So let's say that the speed of light is given by, I have to look for this information up, but let's try to put that apart. You have two systems, two particles that are going to interact inside a collider at
Mm-hmm.
99.999% the speed of light. What
Yep.
relativity says is that that tiny amount of energy that you require to reach the speed of light demands infinite is infinite. So if you want to increase from 99.999% the speed of light to 100% the speed of light, you require the system
We
requires.
do not have the power, Captain.
Okay. Okay,
Okay.
we might have it though. I think we have it. So
That's it's fascinating. It's fascinating. Yeah.
let me get you here to see if you get the notion. So we have particle A and particle B, red and green, moving towards each other at 99.999% the speed of light. If we assume that space is quantized, that space time is quantized, it seems to me that you have uh, no other option than assuming that between one atom of space and the other atom of space, there is some kind of quantum jump, because that is the minimum resolution, the minimum amount of movement that is possible in the universe is for a system to move from one Planck length to the next Planck length. Okay,
Yep.
that would probably require one Planck energy of momentum, right?
But Planck energy is actually an extremely large number. It's like 10 to the 44 newtons. I understand what you're
Yeah,
saying.
because
It's yeah. No, no, I
let's
understand. I'm just letting you know in case you say something like that to somebody else.
yeah,
I understand.
somehow
It requires X amount of energy. Go.
the minimum we have to assume that the minimum energy in the minimum, so far from what I know, the minimum energy in the universe is the amount of energy that takes a photon to move from one Planck length to the next Planck length. So an object that doesn't have any weight still requires a little bit of energy to move from the minimum distance to the next minimum distance. That is not free.
Well, that's interesting because I've considered this every once in a while, but you formalized it much better right there. How does that work?
So let's say that in the very minimum scale, motion is a quantum jump from one Planck length to the next Planck length. So an object has to update its position in space-time. The minimum change that an object can take in space-time is one Planck length by one Planck time. Even if the object stays in the same place, it's constantly updating its own position, at least in time, probably in space as well, because if you have dark energy inflating the universe, the object never stays in the same place. If the universe is constantly growing, an object never stays in the same place.
We're never actually still. Yeah.
Okay. So that seems to be pretty logical. So, in regards to the object and its relation to space-time, there is always a demand of energy because the object is always moving,
Yeah.
because the universe is always inflating, and the relative position of the object with every coordinate in the space-time is changing. The nature of the intrinsic change of the coordinates is what we call dark energy. It's the force that makes the universe expand, but it's also a force that imprints a change in position to any given object in space with regards to its immediate past. So object A is not moving and is apparently in the same position, but dark energy and inflation is always changing its position with relation to every other point in the universe because the universe is growing. Do you agree more or less with that explanation? Did I make myself clear enough in that sense?
I get the bit of your jive. I understand. That's it's go on, go on.
This is nobody really knows.
Well, that's why these are great questions.
Okay, so let's go back. Let's try to go back to this example. We have particle because I'm never gonna end if we continue going deep. But
I was gonna say I'd be able to help you, if not answer at least one or two of these questions, at least give you some resources I think you'll find fascinating.
excellent. So you have particle green, which is about to collide with particle red at 99% the speed of light, 99.9% the speed of light.
Yeah.
We are kind of playing with the idea that any change in coordinates for a given system, the minimum change in coordinates is equal. The minimum change in coordinates for a system equals to one Planck length. That is the minimum amount of space that a system can move in any given direction. If that is the case, in space, it has to do with the fact that space is quantized. If space is quantized, there is no other way to interpret motion other than a kind of quantum jumping from one Planck length to the other Planck length. So you have these atoms of space and a particle. Let's assume that there is a particle as small as the atoms of space. Maybe, like you say, an electron is 20 Planck length by 20 Planck length by 20 Planck length. It doesn't matter the size of the particle. The resolution of motion is one Planck length. So motion is also quantized. If space is quantized, motion by necessity is quantized because the minimum amount of distance is not infinitely small. So it has to go from one Planck length and then teleport itself, quantum jump itself to the next Planck length. So there is a quantum interpretation that has to be run for movement and for motion and for inertia and for momentum. Momentum might be a quantum jump from one Planck length to the other. Objects might jump. The whole system jumps from one Planck length to the other, like an image in a screen does. When you're moving an image to the screen, in the screen, the image is jumping from a given set of pixels to the other set of pixels. That is limited by the refresh rate that you may have on the screen.
At what point is it going to light up? And if we're going to assume we're going to use Planck units as our bounds, there it's like, well, if everything's going to be running at a refresh rate of the Planck time, which is like 10 to the negative 44 seconds, and we're going to be covering distances of Planck length, area, volume, however you want to spit it out, well, that's 10 to the negative 35 meters. And if we're going to use as one of our axioms the principle of least action, which is basically what it sounds like you were saying there, how does it decide which way it goes? Which then gets me, if we're going to continue with the whole screen and energy, at that point, I'm going to have to change it into almost a plumbing analogy, in that if there's these pipes there, it's going to go where there's the least energy or the least things blocking it, because as we apparently know, space-time itself isn't a complete vacuum. There is energy in it.
Let's say, let me use that thought that you brought out in me, that particle A wants to move from here to here.
Mm-hmm.
If motion and causality is already kind of predetermined by the wave function, and the wave function is running ahead of the system and is calculating all the possible paths and then collapsing in the one that requires the least amount of energy and the least amount of updates for the universe, and updates not so much for the universe, but maybe the principle of least amount of energy can be translated to the least amount of atoms of space that need to be refreshed in their properties for a system to translate itself. Let's say atom 1,4 is green, it has particle green in it, and then particle green is going to move to atom 1,3 and then to atom 1,2. Maybe the universe indeed calculates the wave function, runs ahead of the system and is calculating all the possible combinations. And then the one that collapses is the one that requires the least amount of updates for each atom of space. But if this movement, if the update of a given system is limited by the speed of light, then you may have the condition that gravity might distort the position of these atoms, let's say, and then these atoms might find themselves a little bit displaced because some kind of gravitational force was influencing them. And then maybe this calculation, even when this is kind of digital, from 3.4 to 2,3 to 3,1, is quantized. Maybe the relations of the atoms of space with each other changes, and that's why you get gravitational lensing, because light was supposed to move, a photon was supposed to move from here to here in a straight line, but the sun here was pulling these atoms in this direction, these atoms of space. I'm talking about these pixels. Let me use my own language. If a gravitational force here was influencing the relative position of these pixels with each other, maybe they moved a little bit in here. Let me see if I can find it.
There's going to
To
be a
me,
shift.
in my model, space-time distortions might be given by the fact that you have some atoms of space moving with regards to each other. So gravitational lensing is this particle, this particle was supposed to follow this straight line, but now this straight line is not straight anymore because there is an object influencing the pixels, and the pixels, what was supposed to be a straight path now has a little bit of a distortion in it because space-time in itself, the pixels were moved in relation to the original position that they had before or without the influence of the gravitational system. But let me know not
No. I like the way you're doing that because I feel like you're explaining in a much more clear and visual way what gravitational lensing is. Because a lot of folks say, well, it's bending light or something like that. And people like, bending light? That seems kind of weird. Whereas in fact, the effect is more of bending the space time around it, the atoms of space and everything. So, I mean, that makes more sense to me.
It's bending what
Because
was
light is
supposed to
traveling
be
along that
the
path.
most straight path, the least energy demanding path between 2 points is being distorted by the presence of a heavy gravitational force, by a heavy gravitational.
Oh, I totally agree with you. I totally
Okay.
agree with you. Now, can you give me your final question, and then
Yes.
we'll go back and
Sorry.
cover up.
So let me jump straight to it. You have particle green, particle red are moving in this direction from here to here.
Yep.
Here, sorry, from here to here. Let's say they are jumping, doing quantum jumps from one pixel to the other one, and they are going to meet here, right?
Yep.
This one is going to move in this direction. This one is going to move in this direction, and they are going to collide in this point. What I'm saying is, and it depends a lot on the nature of space-time. If a gravitational wave is something that erases or compresses a pixel, then let's say that you have a gravitational wave here. Let me make the cross section of a gravitational wave. Let me put it in purple. Here, gravitational wave in purple. Let's say that you have, this is the cross section of a gravitational wave. And I know that the scales are not the same. The amplitude of the gravitational wave is not one Planck length, but it will take me a little bit more time to explain my concept behind that. So you have the cross section of a gravitational wave.
Yeah.
The question is, does a gravitational wave diminishes what is a Planck length, what is diminishes the dimensions of a pixel in itself, meaning does a gravitational wave make Planck length shorter in this point? You know, this is let's say that this is normal space-time here, and this is zero, being represented by zero, the normal curvature of a space at that given point. And then you have the gravitational wave. This is arbitrary, representing a -1 compression of a space-time. And this is the gravitational wave. This is normal space-time, and this is the wave moving through space-time. So does the gravitational wave at this point make a Planck length shorter? Does a gravitational wave make the jump from one Planck length, they assume quantum teleportation from one Planck length to the next one, less energy expensive because the distance between the pixels is shorter, you know, gravity might be an object changes its trajectory, its motion in the presence of gravity, maybe because the pixels are closer to each other and they demand less energy.
So it would take less energy, so you could effectively either observationally exceed the speed of light, or what happens there?
Let me get to that point. You're almost understanding the concept. So we can assume that gravity distorts motion, not because necessarily space-time is bent, but maybe because the distance, let's call it distance, but maybe because the energy requirements for an object to do quantum teleport itself in a straight path is higher than, no, let me rephrase that, sorry. If gravity imprints an acceleration, a motion in what was supposed to originally be straight path. Let's say object A is going to keep a straight path. Now all of a sudden it's getting close to a black hole, and the gravitational pull is changing the gradient of energy that the object requires to move itself, to propel itself into the future. So instead of following a straight path, the demands of normally the straight path was going to be the less energy demanding trajectory, but due to a given effect, we don't really know why, in space-time, all of a sudden there is a less energy demanding trajectory for the object that is affected by the gravitational object that is influencing the system. But that this requires a longer conversation. Maybe we can do it in the future. Let me go back to this case of and I'm pointing at the screen like if you were seeing me and you're not seeing my hands.
Oh, no, I'm looking at your screen, so.
Yeah, but you cannot see my hands, so I need to use my cursor to show you. But we were on the point that particle red and particle green are going to interact in this point here. Right. Sorry, let me create another layer. They are going to interact here. What I'm saying is, in the absence, in the normal case of particle colliders, particle collisions are taking place in a kind of flat space-time. No, it's not flat because we are on Earth, and Earth has a gravitational field that is distorted by the nature of the mass, but is constant. So when a gravitational wave is coming, the gravitational wave is distorting the normal gravitational field of the Earth. That is exactly what we are measuring with the lasers on LIGO. We are measuring a distortion in space-time. That distortion is...
That's why you had your diagram of having it orthogonally set up there, so you could see potential. Okay, all right, I like that.
So, if a gravitational wave arrives to the system, normally, this is complicated. Normally, the effect of the gravitational wave is very tiny in terms of metric system. It equals of around half of the size of a proton in, I don't know how. It's a very tiny effect, but I looked it up. When you look at the gravitational wave effect that we have felt here on Earth, that we have measured, in terms of Planck length, there's a lot of Planck length of distortion, of compression that we are experiencing.
Right.
So if this is complicated, if at the very last moment in the collision between the two systems, normally, let me try to use an example. Let's say that you have one car that is going to crash with another car. And the relative speed of those cars equals to the change in the distance that is separating them. For example, you have one car going at 100 miles per hour and another car that is going at 100 miles per hour in opposite directions.
Mhm.
The speed of the interaction of those two cars is going to be 200 miles per hour in
Mhm.
classical mechanics. And that speed is given by the change in the distance that is separating between the two cars. If I remove a meter from the two cars, let's say that the two cars are going to crash, and there is 100 yards left between the two cars. If I remove 1 yard from the 100 yards, it doesn't change that much the relative speed of the two systems, of the two cars. They are going to crash at 200 miles per hour minus the change in speed that represents 1 yard less in the total equation. But if the distance between the two cars is 2 yards and I remove 1 yard from the speed, I'm actually doubling the relative speed of the crash, because instead of having 100 yards between each car and I remove one, now it's 99 yards between the two cars. When there is 2 meters, 2 yards between the two cars, and I remove 1 yard, the relative speed of the two cars is doubled because the distance was halved. Do you follow me, more or
So,
less?
that's why you were talking about before, if what was it? You
That's
you
why it's
you you were
important
talking about
to
that earlier about
quantize
before you removed that.
distance.
Yeah.
Go ahead,
Oh,
say.
no. If basically we're talking about their future, basically we should consider the future rather than the past.
Uh-huh.
That's
Instead
why
of
you were bringing
measuring
that
the
up. Okay.
speed of each car, you are measuring the speed at which cars are going to collide. This is a little bit problematic. It has to be put in general relativistic terms, but this is just an example. In any
No,
case,
no, that's interesting. No, because now just thinking about it in my mind, I'm like, well, would that really make a difference? But I am considering it with my Bayesian priors, basically like, okay, if we're looking from the past, it shouldn't make a difference. In the quantum mechanical sense, I'm like, well, that looks like it's going to make a difference. But now I'm like, if we are going to assume that, and I were to hold that true, I mean, relatively, those cars are now oh, that is interesting.
so it depends if the universe. There are a lot of difficult questions that this implies. In any case, let's go back quickly to the particle example, and leave that behind, and let me not torture you anymore.
Okay.
So in the case of quantum mechanics, if we are experiencing some kind of quantum jump between one pixel to the other one, and the gravitational wave affects the amount of energy that is required, or the amount of, maybe the energy is related to how far from one pixel to the other one the object has to jump. There is a lot of things that need to be considered here. It all depends on the nature of space-time. Maybe there is no answer for my questions. I think that I'm on the very verge of there is
I think you're
no.
on the right track because n equals force times distance.
Mhm.
That's and then force is mass times acceleration. So, oh, sorry, you bring
So,
your thing back up.
well, that is a classical mechanic approach, or classical mechanic interpretation, I believe. But if the trajectory of, let's say, light is changed, not so much because of a distortion in the geometry of a space-time, but a change in the least energy demanding path for an object, because maybe it implies a distortion of space-time. Maybe the pixels are closer to each other near a gravitational wave and a gravitational presence, and maybe an object that exerts gravitational wave, gravitational force. Maybe the nature of gravity is the amount of distance, or the amount of energy that that demands that there is between one pixel and the other. In any case, if that is what is going on in the background, then a gravitational wave, you have to assume at some point that if space-time is quantized, there is in fact no infinite limit to the energy that the collision at the speed of light demands. Because if there is a limit for the amount of updates that a position of a system has to satisfy, I'm trying
if there is a limit on what can actually happen, how infinity? Because there are limits.
Let's say that at 99, I'm going to try to finish this. This is very demanding for you as well, I'm sure. Let's say that in the very last moment of the interaction, these two particles, in reality, before a collision, there is a point in which only one Planck length is separating the two systems. I mean, the collision happens when the last Planck length is covered by the system, right?
Mm-hmm.
At some point in the interaction, there is just one Planck length left separating the two systems. So the collision happens when that last Planck length is zero. So delta D between the two systems eventually goes down to zero. And these two systems have to meet each other at a given pixel in space. So what I'm saying is, if the nature of a gravitational wave is that it diminishes the amount of energy that is required for one system and the other one to update their position, that might, it's difficult to put it because in my mind I think in terms that might not be familiar to you, but are you following?
Don't mind me, I'm just grabbing an orange.
Okay. Basically, if the last Planck length is compressed by the gravitational wave, the energy demands might be less, and the energy injected into the system by the gravitational wave might be the energy that is needed to cover that last Planck length at the speed of light, is what I'm saying.
Now would that energy be less or would it be more? Because now you're literally compressing space-time itself. Again, it's a fascinating question because again, if there is a deformation, like if that's stretched or compressed in a way, we would normally think that okay, it'd be easier to reverse that distance, so it makes sense.
So
But
Einstein said that there is no difference between falling in a gravitational field and experiencing acceleration. So if particle green here is here and particle red is here, and this is in purple is a gravitational wave, and there is a difference in the gravitational potential that is imprinted by the gravitational wave, these two particles will need an X amount of energy to collide in a relative flat space-time. But if space-time at that point is less than flat because the gravitational wave distorted the space-time and made the distances shorter, and probably that's where I have a question. Time itself was distorted. Maybe that last few Planck length in the interaction happens faster in the presence of a gravitational wave that is compressing those few last Planck length.
So that's why you had the experiment set up to see, depending on how the gravitational wave interacts, if we see potential faster than light effects.
What I'm saying is, normally all these interactions happen in a relative uniform gravitational field that is not affected by a gravitational wave. So any distortions in the distance between the two particles, we have to assume that they are gravitational wave going everywhere all the time. But if you make to cohere a gravitational wave that is moving in the same direction as the interaction is going to happen, and the interaction happens in the moment where the value of the gravitational wave is imprinting an extra acceleration to both systems. Remember that Einstein said that gravitation equals acceleration towards the gradient of gravity. You have a gravitational pull equals acceleration. Normally, in our systems, that gravitational pull is perpendicular to everything we build because the colliders are horizontal to the pull of the Earth. We build colliders in the surface of the Earth, and we have the gravitational pull pulling inside, pulling perpendicularly to the way in which the particles are moving toward each other, because because the collider is horizontal, it's built horizontally. But if you have a gravitational wave incoming in the same direction in which the collider is oriented, then you have a gradient of gravity that might imprint an acceleration, an extra acceleration to the system in itself. So what I'm saying is that if you manage to make, atoms and atoms are manipulated in this same way. You have an electromagnetic wave that is making coherence with the position of the atom, and the atom is being held. You can hold an atom using coherence in electromagnetic fields. You can use the difference in potential in an electromagnetic potential to keep an atom in a given place. So what I'm saying is more or less the same. If you have a difference in gravitational potential imprinted by a gravitational wave in the moment in which the two particles are going to collide, maybe that extra bit of acceleration that results from the distortion in space-time imprinted by the gravitational wave is enough to cover the last Planck length at a speed greater than the energy that you imprinted on the particles by your own means. So energy is given to particles by an electromagnetic field that you are generating on Earth. But there is another source for energy, and that this is the principle behind the Alcubierre drive, that if you distort space-time, you don't need to imprint momentum to an object because the object will gain energy due to the distortion in space-time.
It's accelerating because it feels like it's falling. It's the principle of equivalence.
Exactly. So if you consider the relative motion of these two particles as falling, there is no difference between falling and being accelerated. No difference between moving in a gravitational field because you imprinted momentum to the particles using an electromagnetic field, or because the particles are moving because the space-time is distorted. So the origin of momentum is independent. You can give momentum to a particle by accelerating it using whatever means you have, or you can give momentum and motion to a system by distorting the space-time in which the system is embedded. So thinking maybe if you want to push the particle using energy, you have to give infinite energy to the particle. But if the source, the frame in which the particle is going to move has the difference in energy required to achieve the speed of light, let's say you imprint 99.999% the speed of light to a particle via electromagnetic fields or whatever means you have. That is true in a relatively uniform gravitational field. But if the field has a small bump, positive bump in it, or negative bump, whatever you want to see it, that energy that would amount to 99.999% the speed of light in a flat, relatively flat space-time, in a curved space-time might be higher if it happens in the right time, in the right moment, right when you have a very short amount of Planck length left between the two systems. Like in the example of the car, the speed, the relative speed of two systems is not given by the origin points of the systems, but where in the future those systems are going to interact, and the delta in the possible futures. So basically, at the end, everything comes down to is a speed between two systems should be interpreted as a change in position regarding the past, or as a change in position regarding the future, just like the particle that is about to fall in the black hole.
These are these are the questions and the propositions that I totally love, just because this is even something that Kali had brought up the other day. Just when we're considering things from this, like, why do we consider it this way? It's just the way everyone's done it. But does it make a difference? Like, okay, it's like proton we view as positive charge, electron is negative charge. Why? Because good old Ben Franklin at one point was like, oh, this is the negative, this is the positive. But when we actually investigate it, to be fair, proton should probably be the negative version and the electron should probably be the positive version. But it shouldn't make a difference, should it?
Why, in quantum mechanics, you have to factor all the possible futures, and then they collapse into the present if the future is not important. So the problem, the great problem between GR and quantum mechanics is that GR projects position and momentum from the past, and quantum mechanics is always coming from the future to the present.
See, I'm not sure. I understand what you're saying. Like, is it predetermined? That's something that I tended to mostly believe before. I didn't want to believe it, but I'm just like, I couldn't get away with it. At this point, I'm not sure, or even I'm not sure it really even matters, because my intuition is that it's computationally irreducible. So I mean, we can just say whatever's going to happen, but at least if we believe that something's going to happen, we're going to be more likely to take action. And if we're more likely, basically, if we believe in free will, we're probably going to end up in a probability where we're going to be acting like we have free will. That's kind of the gist of what I'm saying. Do you have a final question before I can play?
Yeah, thank you for your patience, extraordinary patience.
No. I've learned a lot. No, this is why I like doing this. That's why I do a lot of these chats and everything.
So you had a question to say?
Oh no. I want to get whatever your final question is, and then I think I might be able to help you with some of the stuff.
That's enough torture for you today, my friend.
I got to premiere my other video and then go out for a run and stuff.
Okay, bro. Great training system. I like the work that you have done a lot. I'm now myself. I haven't eaten anything today. Right now, I'm fasting since the morning. I haven't drink anything but energy drinks. That might be.
That's not a good. Well, I say that's not a good thing, but I'm doing the exact same thing.
Okay. I'm burning fat right here. I'm running on ketos right now. On keto.
Okay.
So this might not be my best moment.
Your final question.
I changed a lot of diapers today, so maybe in the future I'll be more coherent.
No worries.
Thank you, brother. Nice meeting you. I'm gonna write you to see if I have a copy of this. I'm gonna keep it for myself. I'm not thinking in polishing anything, but maybe, like you said, you can orient me a little bit, and maybe we can eventually talk to somebody who has who is really qualified to answer some of these questions.
So give me a question, and then I want to show you two quick things.
Do you want a question from me regarding this
No,
problem?
no. Do you have a final
Okay.
question that we could get on this recording so I could look back and you could look back on it?
Let me try to formalize it quickly in my mind to say it in the most coherent possible way, most standard way possible. Is the amount of energy required for a system to traverse through space modified by the presence of a gravitational field, or does a gravitational field actually distorts space-time and distorts the trajectory? So maybe you have, let's say that you have a bar 1 atom thick. Let's say you have a million atoms aligned with each other in flat space-time. If I move those atoms close to the heavy gravitational field, will that bar distort itself and the atoms would not be aligned in a straight line anymore? Or it's just that that in reality space-time, we are interpreting space-time as distorted because we can see light bending, but maybe what space-time in itself didn't change, and it's just the least energy demanding path for light what changed. And you like I have said before, or like I saw somebody say before, for the lightning strike is following a straight path. To you, it looks like it's very
Jagged and everything.
jagged. But for the lightning itself, he just followed the straight path of least electrical resistance. To you, it looks bent from any given observer. But if you ask a lightning, he will tell you that he followed the straight path of least energy.
Lightning is following its lightning path.
Exactly.
So that's a great question. It almost reminds me of a chicken or egg question, and it's that it sounds like to formulate it in a way that maybe Professor Wolfer may say, again, I'm a total narcissist, yada yada.
Yeah, go ahead.
It's basically like, does gravity lower the amount of energy needed to traverse a distance? Because at that point, that basically leads to the whole concept, to my knowledge, between any type of Alcubierre drive, warping drive, because it's like, okay, we don't have infinite energy, but if we could find a way to
it's cheaper for the system to move forward.
Exactly. Then it would require finite energy
demanding in front of it,
right?
And that results in motion. An Alcubierre drive moves forward, maybe not because space-time is bent, but because there is less energy demand for the object to move forward than to stay in its place.
Cool.
Okay, maybe it's more less of a geometric problem and more of an energetic problem. Energy gradients.
So what we're gonna do is I'm gonna show you a couple of quick things next to both of these. Going upon the entangled particles, there was I mentioned the Unruh effect because that's the Unruh effect that's named after Professor William Unruh.
I checked it once, but I don't remember it.
Yeah, no, PBS Spacetime did a pretty good video on it at one point. I came across a lecture he did. I did a quick video on it, but there was a fascinating point because at that point you're describing what they call, I believe, unitarity. And I like to do my light trolling and just find myself bookmarks.
Yeah.
And nice. I should be sharing. Let me know if you can hear it.
I just like to stress that even if we didn't go in mind, all of these high L modes have some probability that's not zero to tunnel through the angular momentum barrier.
Yes.
So their wave function is going to develop a tail outside of the black hole. And if we assert that these are in the Hawking state in the infalling vacuum, then that alone would destroy unitarity, if only by a little bit.
I don't have the concept of.
I don't mind unitarity being. I don't think there's anything terrible about unitarity being destroyed.
I know, but why did you
So-
give such a long talk in that case? I mean, if we
he
don't
went
worry-
on for about
we
an
don't worry
hour
about
and 10 minutes
unitarity,
at
they're
that point, and basically what I'm hearing there, this is a question that physicists haven't gotten to the bottom of yet.
Mhm.
Basically, think of like a black hole potentially having a firewall, in
Okay.
that whatever goes in, the information is there. Maybe it goes out via Hawking radiation because of those entangled particles or whatnot. Now, I'm actually not sure myself which one he's saying there, because he delved into a lot of topics during this lecture. I'll post the link over here in the chat. But it's a fascinating thing, because you could interpret that a couple of different ways. In that, okay, so if there is a firewall, do we necessarily know what's going on? Or are we just taking that thing that's imprinted on the surface of the black hole, because the information is encoded on the surface, which is a fascinating thing itself, and then we could kind of measure, and then if ER equals EPR, we could kind of get something for that? Or is there a way for something to tunnel back through some form of information? I don't know. Again, this was a fascinating lecture.
I'm gonna check it out. I'm gonna try to get familiar with the concept. And now I'm gonna give you one last thing. Imagine that a particle is a surfer. A surfer on the sea. The surfer requires energy to move in a flat sea. But if the surfer is falling in a wave, the surfer doesn't need to expend any energy, because the wave in itself is providing the difference in the energetic difference. I mean, let me try to formalize it a little bit more. A surfer in a flat surface on the sea needs to expend energy to move, to translate itself in space-time. But if the surfer is in a wave, the wave is imprinting momentum in the surfer. So a surfer is always falling in a wave, is always falling, and he's moving in the X plane, but it's not really moving in the Y plane. So the difference in potential, if a relativistic particle is coming at nearly the speed of light, and it founds a gravitational wave in which it starts falling in the gravitational wave, is gaining an acceleration.
Right.
Like a surfer will do.
It's surfing. The surfer wants those big waves because they're effectively falling, even if they're not falling.
So that might be not a good analogy, but I think that is what happens.
I think you're on the right path. Now, the question we would take from that is there a particular geometry we could identify that may help explain this? I'm going to make a claim, number one, because I'm totally biased. Number two, I totally already made t-shirts as well. But I'm going to make a claim here. I'm going to say something like this.
Okay.
May help explain this. These cutouts are just for visualization. This is the complement of what's known as the hyperbolic figure 8 knot. And when you were talking about all points being connected in some way, it made me think of a particular part of a video I had done with one of the founders of the think tank that I recently joined, the Physics Monastery. I'll just play a quick 30 seconds from this.
Okay, there's an interesting, the grid doesn't allow these operations to be perfectly symmetric everywhere, but they work most places. So we have to make sense of why this map works on this metric. What is the actual metric? Well, some people would like to say, well, if we could find a way to twist the metric so that it's making sense, right, then it would make more sense to make sense of the math. But if you twist a metric, then all of its points are screwed up, right? However, it's been shown that there are ways, interesting ways, to rotate a metric several ways so that its points, 1, 2, 3, 4, all the grid points stay the same, but all the connections in between don't, right? And what operator do we need to do that? The gamma function. All
I'm not
right.
familiar with the mathematical terms.
The gamma function is a mathematical function that it does occasionally get used in physics, but apparently not as actually. I think this is how Leonard Susskind actually originally conceptualized string theory, because somebody had come up with something with a gamma function in the numerator and gamma function in the denominator, and that's kind of how he was able to kind of map it out to something else. And rather than using the harmonic oscillator, the spring attachment, he's like, well, if I used a string, this would work. And that's kind of how string theory was born. The claim is, to my knowledge, and again, I'm just an intern, there's a way you can map. This is a double cover, what's known as the Giesking manifold, which there's like no actual pictures on the internet of that particular manifold for some reason. It's basically just a tetrahedron, basically a three-dimensional triangle. It's folded over. This object, the cutouts are just for visualization. You can represent it as essentially a three-sphere, basically just as a sphere, and that's a double cover of that. It is a Kleinian structure. Its first homology group is the integers. So I'm not a mathematician.
Terms at all.
Yeah, essentially the claim is, because the gamma function, the way it works, I think it's equal to like a 0.68 and also negative 0.68. So that allows you to attach whatever tensor, operator, however you want to conceptualize it, whatever the right term would be, you have the ability to connect pretty much everything.
Okay, yeah, so it allows for multiple topologies. The topology is infinite, any configuration.
I mean, that's, again, I'm probably butchering that.
Me too, me too.
Yeah, I would suggest the way I came across this is I have a playlist, and I think I changed it to my first video. It's 20 minutes. If you're interested in exploring some of these things, I also have a bunch of links.
Okay.
But the only reason why I came across this is because somebody else on the internet, basically somebody like you, that just kind of reaches out and to me and everything, noticed that there was a pretty smart physics gentleman that was putting out some content on YouTube. I listened to something that premiered April 6th of last year. I know it was April 6th because I was just out on a run. I'm listening to this thing. I'm like, Platonic solids, great claims. Sounded like geometric unity, basically. I'm like, but greater claims, because he was actually putting out the mathematical numbers and notation. I'm like, well, that's kind of cool. If half the things he's claiming are true, this is revolutionary. And then the next day on April 7th, they came out with the muon G2 results, which is the big hubbub about physics. New physics. We don't know how it happens. So I hear that. That's cool. And since this gentleman video premiere was fresh in my mind, I'm at work. I tweet at him at work. I'm like, does this help your model? He's like, yes. I come home. I look at the Fermilab results that were published. I look at the numbers. I go back to the video that had premiered the day before. I look at the numbers and I'm like, Duman nailed it. This guy predicted the muon G2 results. But like, he just personal private think tanks. He's not part of like any like major university or anything. So I started listening more and more. I've interviewed him a couple of times, but long story short is somebody else had noticed the discussion going on the internet, and they found an equation that could predict the fine structure constant out to like 7 decimal places, which that's really good, because like we have no way to geometrically predict the fine structure constant. So he looked at it, and then he's like, this is very interesting. And then he was like, wait a second. He rewrote the equation a little bit, and then he's like, what if I assume this was true? What would I have to modify the equation by to actually get it to be the fine structure constant? The number that he just put like minus y. The number that came out was the number on the t-shirt, which happened to be, oh, I got it the wrong way.
Uh-huh.
But very simple equation. They call it the hyperbolic vortex equation. Number that comes out is basically, what is it? Let me stop that. Boom.
Mm.
The number is, what is it?
Yeah, it's cutting it out.
Yeah, it's,
No,
hold on, there we go. Okay, so it's 1 over x, or j in this case, plus x cubed, divide by 2 pi, equals I to the I, raised to the negative pi divided by 2. So it's basically this one, it's basically divide by 2 pi. So basically a circle one way, and then pi divided by 2, a small circle the other way. That MP, that's the Planck mass.
Okay.
So,
Yeah, I need to learn a lot more math in order to be able to interpret formulations.
right. No, don't do it. I was like, blah, what? And that's why I literally started learning Wolfram Alpha, because I just go on to it. I plug the number that he gave me in there. The first answer, that's the number that basically Professor Feynman said was the true fine structure constant. But I just take that, I do the up caret 2, raise it to the second power. And if you look up the fine structure constant, that looks like the fine structure constant. That was how I kind of came across this stuff.
Mm-hmm.
And I hear folks say, well, you're theory anything unless it matches experiment. So I hear a lot of smart people say that, and I'm like, happened across Lynn, who his model agrees with experiment. And the best part is, maybe it's a math trick.
Yeah, it might be.
I don't think it matters, because he computed all this using Wolfram Alpha too.
Okay.
Like, he found a method to search the computational universe for just very simple, very beautiful equations that seem to represent our world. And again, I'm not saying it's right, but it's interesting. So if you have a chance, I go over a little history with some links. It's on my YouTube channel.
I'm pretty sure that I don't have the mathematical background to.
You don't need it for the main video on my channel. I basically just go tell the story. It's a story about how the heck this happened, which was actually inspired by Dr. Eric Weinstein on the Joe Rogan Experience, because I'm like, this is fascinating. That's how I basically got into the whole Wolfram thing, ran into you and everything. So it's funny how the causal structure's all interwoven too.
It's very interesting.
But I'm gonna pop out. Thank you for showing me the stuff about the Aisling and stuff, because I think this might help explain a lot. But let me end the recording.